Morning.
Good morning.
Good morning.
Good. How are you?
Good. Yesterday I sent you my final project.
You sent me the draft already. I haven't seen it. But I will. Why have I been?
Yeah.
I will. But it takes a few days because I'm in market. I haven't seen it.
Oh.
Yesterday I was teaching. Today I'm teaching. I need to mark big class.
Okay, that's right.
I will read it precisely and I will send it to you.
Okay, but I was struggling with the grammar. I don't know if something.
What class?
I was struggling with grammar.
The grammar?
Yeah. But I just a lot of it.
Okay. If
If you have any comment for the grammar.
sure. You will receive an email from me, but not today or tomorrow. minutes.
Okay, that's fine.
No,
Monitor.
no.
Just having a quick morning breakfast.
Don't be rush, it's okay, just take your time.
When are you gonna mount the processor?
I will tell you in 3 minutes. I'm just waiting for 9 o'clock. Good morning, everyone. And first of all, Happy New Year. I hope all the best for all of you and your loved ones. I wish we will have a better year than last. Just to have an overview of what we are doing in this term, the term 2, in this module. As you remember, we went through some topics we did from part of the report group. And we left a little bit of that for the part 2 because we didn't teach this one, matrix analysis of P. So part of the coursework is the second part. And as you know, we are at the middle of deformation-based methods. We went through truss structures. Now we are going to go through beam elements. And after that, we are going to go through frame element. So we will cover truss, beam, and frame. And when we finish this, we will start something completely new, which is about dynamic analysis of structures. Whatever we have said from the beginning of the semester, previous semester until now, until the end of the stiffness method, is some sort of static analysis, right? But then we will move to dynamic analysis, which is quite more advanced and more realistic than static analysis. So what you don't know is just to increase the performance of the module and to give you some better distinction between different parts, I decided like this. We will finish the stiffness matrix in 2 or 3 sessions, okay? And the final exam in May, I think, will be from the beginning to the end of stiffness matrix, stiffness method, okay? And the rest I will teach you will go to the second part of your coursework. So it's the
exam, there will be only one topic.
Not one topic. From the beginning, we have energy methods, we have everything we have told you from the previous semester until the end of stiffness method, which will be in 2 or 3 weeks, right? That would be the exam, okay? The rest, beyond that point, will go through the second part of your course. So it gives you some flexibility, better time management, just to know what part you need to study for the exam and what part you need to do for your second part of your course. And for other reasons, because it's very difficult to combine an exam in 2 hours for static methods and dynamic methods. And for the dynamic methods, it's really difficult to do with hand, so we need to do with computers, stuff like that. So for the second part of, so for majority of the second term, we'll go through the coursework, but this part, the stiffness method, still stays for the exam. Okay. However, you have something for the coursework. The beam is for the coursework.
What about final difference method? Would that be in the exams of?
No. Final difference is a numerical method. Numerical method cannot be in the exam. And when we finish the stiffness method in a few weeks, in a few sessions, I will design a mock test for you. It doesn't contribute to your final mark at all, but I will give you some sort of exam, some sort of questions that is somehow similar to what you will see in the exam. We can do it virtually. I can give it up via Moodle and you will see the answer a few days later, or even we can do it in the class, but we will decide it later. However, just get prepared for a mock test from the beginning to the end of the stiffness method. And it's just a kind of mini exam for you just to get prepared. It's not something contributing to a final. So just stress-free and try see it as an opportunity for yourself to train yourself and get prepared for the final exam. So this is my plan for this semester. And if you have any question or comments, just contribute. So
Only have one question. Why did the proposal go?
for the coursework, I forgot, sorry. For the coursework you submitted, you will receive my feedback around early February. Okay, I haven't looked at them because I need to mark a huge class of 150 students for master degree. And I'm struggling with that now. So when I finish those 150 coursework and the exams for that class, because they are not two double terms, they need to finish everything that the marks should go through the PAP meeting. After that, which means somehow end of January, I will start your coursework and you will see my feedbacks and your mark almost early February. Okay? So don't be in rush and just take your time. Nothing is going to happen until then. And you can use the comments for the next part of your course if there is any. Okay? Anything else? Comments, question, jokes for the new year? Okay. If not, we can jump into the lecture.
Sorry,
Yeah.
sorry to make you repeat it, so the exam was gonna be from energy method?
Yeah, from whatever we said from the beginning, because we said something about truss structure, instability, stability, energy methods, integration method, and stiffness method, which are this. Okay, principally it's about truss structure, stability, energy methods, integration method, and stiffness. That's all.
Is that just mock or would it be for the final exam as well?
For the final exam, it's like this. For mock test, it's a mini test. I just give you probably 1 or 2 questions. I have to choose some topics, but it doesn't mean if I choose some topics for the mock test, it's the same for the final test. You know, the final test is from everything until the end of the stiffness method. Okay. excluding the, what was it, finite difference. Okay? Because it has been a long holiday, maybe you have forgotten some part of truss structure, but if it's true, just please go through the truss structure, which was the last session of the 2022, and review it. If you have any problem, we can discuss it next week, for example. And this is for beam structures, and we start with this. It's a beam element, near end and far end. Exactly conventions we used to do for truss elements as well. Truss element is kind of element that has only one axial force in it, either compression or tension, right? But beam element is a kind of element which has bending moment as well, shear forces as well. Shear forces and bending moments are not present in the truss structures, but they are in the beam elements, right? But usually beam elements do not have axial forces. So that's the difference. If it has everything together, it would be column, it's not beam, right? So we anticipate a beam element has internal shear forces and bending moments, not too much axial forces. So for that reason, we put here one shear force, one bending moment, one bending moment. But to be consistent with a defined convention of the coordinate system, we need to define a coordination system. So assume that we have a coordination system like this, x prime and y prime, okay, or x and y, whatever you call it. With this coordination system, we have basically 4 degrees of freedoms and 4 end forces. I mean, at the near end and the far end. One shear and moment here and one shear moment there. The near end and the far end, okay? When we have a shear force and a bending moment, it means that this end, every end, can go up or can have these deformations, right? Basically, in the plane, every point can have 3 deformations, x, y, and rotation. We neglect about this one because we don't have too much axial forces. In the frames, we can do different, but here, we just neglect about axial deformations because we know that we don't have too much axial forces. And really, they are negligible. Axial deformations are negligible. Why? Do you remember any place that in this module, we talked about this fact that the axial deformations are negligible? If you remember energy methods, it had 4 different integrations, one for axial force, one for bending moment, torsion, and shear forces. Once we did try to solve some sort of examples to calculate the integration of axial forces, and the amount of value was somehow negligible in comparison with the integration corresponding to the bending moment. So we can really ignore about the deformation along the x-axis, which corresponds to the axial deformation. So we assume that in each end, we only have one deformation along y and one rotation along z. Okay? If we define z like this, for example, right-hand side, this is the axis, right? So that's why the convention for this element is in agreement with the X and Y and Z we define. So these two are from down to top because it should be along the Y-axis. And these two rotational deformations or bending moments in terms of forces are in agreement with Z. They are counterclockwise, right? Here and here. So we have 4 forces at both ends corresponding to 4 different types of deformation. 2 vertical deformation at both ends and 2 rotations at both ends. Just in agreement with what we have for X and Y and Z, right? So each beam element has 4 degrees of freedoms and can have 4 internal forces at both ends. 2 shear, 2 bending moments, right? So how many elements you have in your structure, just multiply it by 4, you will get your degrees of freedoms. Or, no, this is a wrong statement. How many nodes you have, not how many elements, because the elements are connected to one node, for example. How many nodes you have in your structure, just multiply them by 4. Sorry, this is again wrong. How many nodes you have in your structure, multiply it by 2 is the degree of freedom of your system. In any kind of beam structure, if you have a continuous beam, you have many beams connected together, just count your nodes and multiply it by 2. 2 means 1 vertical, 1 rotational. That would be the number of degrees of freedom in your system, right? It can be demonstrated, it's in your book. This is coming from your book, it's on the Moodle resources and materials section. You can find it simply. You can find it there that this is the matrix, this is the stiffness matrix. The stiffness matrix. What was the stiffness matrix? The stiffness matrix correlates deformations to the forces. It's exactly, remember, we were talking about F equal to K delta. This is a formula for simple spring, isn't it? For simple spring, we had F equal to K delta, right? So if you remember, for the truss structure is the same, here is the same, for the frames will be the same as well. K is not a scalar, K is a matrix. Because we have 4 degrees of freedoms for this element, these are deformations, dn y prime. dn means deformation at the near end along the y prime axis. dn z prime, deformation along near node, which is here. We have near node and far node. Along Z prime is rotation. Deformation along the Z prime means rotation. Rotation is a kind of deformation anyway. dfy prime, you interpret it for me. dfy prime, Shamsuddin, what does it mean?
Sorry?
dfy prime, what does it mean? Deformation of? Along? Along? He just wake up. This is a best way to wake somebody up. D means deformation, okay? F means far end. This is far end. This is near end, okay? Y prime means the axis Y prime. Axis Y prime is vertical. So it means this deformation, okay? What does dfz prime mean? Deformation. Repeat after me. Deformation. F, what does F mean? Far end points. Point the right point. Z prime means the axis Z prime. Z prime, this is Z prime. So it's a kind of rotation, right? So we have 4 kind of deformations. 2 of them are transversal along the Y prime, and 2 are rotational 2 are for the near end, 2 are for the far end, right? Each of these deformations have corresponding forces. This means force, Q means force, along the near node, along the y prime, means this one. There we have Q and y prime and V and y prime together here, means this is the shear force and the deformation along this is V and y prime. Deformation near end and y prime, right? So this is connected to these are together. These are together. Why? Deformation near end z prime, force near end z prime. These are all forces equal to K delta. These are all deformations. What is this? Deformation far end y prime. This is force far end y prime. This is deformation far end z prime. This is force far end z prime. What does it mean, force far end z prime? What is the force in the far end along the z prime? This is a bending moment. Force along z prime is a bending moment, right? Force along the y prime is a shear force, regular force, right? We can call force to anything, regular forces and bending moments. All of them are forces. Okay? So all the deformations are listed in the right-hand side. All the forces corresponding to them are listed in the left-hand side. F, vector of F, vector of delta. In between is a 4x4 matrix. It can be demonstrated. It only depends on the specification of your element, E, I, L. So we don't have anything else. For this one, we have, for this matrix, we have only E, I, and L. E is module of elasticity. I is second moment of area or inertia. And L is the length of energy, right? We don't have anything else. So the between matrix only depends on the characteristic of the element, material and geometry. So each element has a specific material, section, and length, okay? Which is usually given to you at the beginning of the example. So for any kind of element, for now so far, for any kind of element, we can follow this formula and write the stiffness matrix like this for that beam. We want to do it in an example which has very simple connection of two beams together. We want to repeat this for two beams in an example, which are connected together. Just, I will refer everything to this. We need to repeat it 2 times for the 2 different elements. Let's go for the first example for the beams, which is example 15.1, which means the first example in chapter 15. First of all, try to understand the question, especially in the exam. When the exam, for example, you got your papers, don't rush to write whatever comes to your mind. Okay, just first read the questions, understand them, and then try to start your answer. At least 30%, sometimes 40%, sometimes really 50% of a correct solution relies on your strategy at the beginning of the question to fully understand the question, then start to answer. Okay, so the question says, determine the reactions and the supports of the beam shown in this figure. EI is constant for everything. So we have a beam, a continuous beam. It has a simple support here, and a roller support here. We have two elements, this element and this element. Like what we have done in the truss structures, first of all, we need to number the nodes and the elements, just to understand what we're talking about, because degrees of freedoms are most important thing to be understandable at the beginning of the graph. So we need to number them like this. And this numbering is really up to you. It's arbitrary. There is no force what kind of sequence you're following. Okay? Just like it, but for each node, we have three nodes. 1, 2, 3. This is node, this is node, this is node. We have 3 nodes, right? For each node, for each 2 nodes, when they connect together, you have an element. So this is element number 1, this is element number 2. And this arrow means I'm assuming it's coming from 1 to 2. 1 is near end, 2 is far end. Okay, just I want to be compatible with that previous slide formula. And this arrow means I'm coming from joint 2 to joint 3. So joint 2 is near end and 3 is far end for this element. Be careful for which element you're talking about. When you're talking about this element, 2 is near end. When you're talking about this element, 2 is far end. Okay, one joint can be near end for one element, can be near end for another. So those arrows shows from near end going to the far end. So we know how to use that previous slide formula for each individual beam element, right? So these are just numbering the nodes and elements. We also need to number our degrees of freedoms. As I told you, we go another color. As I told you, how many nodes we have multiplied by 2, we will get the degrees of freedoms. We have 3 nodes, we will have 6 degrees of freedoms, right? And you can number them arbitrarily, it's okay, whatever you say. But for each node, remember the previous slide, for each node, we have a degrees of freedom vertically and rotationally, right? Because I'm assuming it's X prime, it's, for example, Y prime, and this is Z prime, just to be compatible with the previous slide, right? So this is 1, this is 2, this is 3, this is 5, this is 4, this is 6. And really doesn't matter what kind of number you do, just number them from 1 to 6. Because we have 3 joints, multiplied by 2, you have 6 degrees of freedom. Or in other words, for each node, you need to have 1 vertical and 1 rotational degrees of freedoms, right? So we have 3 nodes, we have 6 degrees of freedoms. Don't worry about the numbering, because if you do another sequence of numbering, they will be rearranged when we assemble the stiffness matrix. At the end, for example, you will find deformation of 1, 2, 3, 4, 5, 6. If you number it in another way, you will find this one, that one, this one. Okay? Just this is a numbering. So if somebody asks you what is the deformation along the y-axis for this point, if I'm different in numbering from you, I will look at my final deformation vector and pick up the third vector to answer your question. You will pick up your fifth vector and answer my question. Because your fifth degree of freedom is dedicated for this, for my case, my second or third number is dedicated for this. This is just the matter of numbering. It doesn't matter what kind of sequence you are, but you need to be consistent with what you are defining at the beginning of the example, right? So we have numbered our joints, nodes, we have numbered our elements, and we have numbered our degrees of freedoms. We have 3 nodes, 2 elements, 6 degrees of freedoms, right? With this definition, we can go to the previous slide. Just, we want to repeat this 4x4 matrix, for element number 1 and element number 2. Just be careful about what degrees of freedoms they should be accounted for. For example, here, K1 is the stiffness matrix, that 4x4 stiffness matrix, for element number 1. Element number 1 is this one, corresponding to degrees of freedoms 3, 4, 5, 6. Just to remember, I write them 3, 4, 5, 6. 6, 4, 5, 3. These 6 and 4 are for the near end. These 2 are for the far end, just to be consistent with the previous one, right? I think the green light is not a good color for writing, is it? Do you see it clearly or not?
Not really.
I think we change it. So this is near end, this is far end. This is near end, this is far end, just to be compatible with the previous slide. I'm just putting EI and L into the 4x4 matrix of the previous slide just to come up with a 4x4 for the element number 1. For the element number 2, we have K2. This is near end, this is far end. This is near end, this is far end. See, for the near end, we have 5, 3. 5, 3. Remember, in the previous slide, for the near end, we had translational deformation, rotational, rotational, far end, right? I'm just following the last slide 4x4 matrix. And remember, these 4 numbers are not inside the matrix. They are just for my hint. I just want to remember what I'm talking about. This is your 4x4 matrix. These numbers are just some hints for myself, just to beside my matrix, just to know which degrees of freedoms they are corresponding to, right? So, are you with me until now? Any doubts how we calculated these 4x4 matrices? We just put in numbers into the previous slide 4x4 matrix to come up with stiffness matrix for element number 1 and element number 2, right? When you assemble your stiffness matrices, you can assemble the whole structure stiffness matrix. What kind of dimension the whole structure stiffness matrix should have? When I'm talking about the whole structure stiffness matrix, it doesn't mean for a specific element, it means for the whole structure. The whole structure has 6 degrees of freedom, isn't it? So, exactly equal to the degrees of freedom, the whole degrees of freedom, your whole stiffness matrix dimension should be. This whole structure stiffness matrix should be 6 by 6 because we have 6 degrees of freedoms, right? Just write a 6 by 6 degrees of freedom matrix like this, full of 0. Forget about the numbers. Write the 6 by 6 stiffness matrix full of 0. Okay? Nothing inside. And go to the, for example, go to a stiffness matrix number 1. Okay? Look at your stiffness matrix. Please, just for a second, don't write anything. Listen up in this section is very crucial. Look at this. I will repeat it for this one and this one. Look at the first number, 1.5. And be careful, we have EI at the back of the matrix, but we have EI at the back of the matrix for the next one. So we can have EI here, don't worry about that. But if it was different at the back of the matrices, you should bring them inside. Or, you know, if you have 2 EI, just bring 2 inside. Try to have something similar for both, but we put EI here for the whole, okay? We have 1.5 here. Okay, this 1.5 belongs to the degrees of freedom 6 and 6, right? I'm using my hint, 6 and 6. This 1.5 should go to the bigger matrix in the cell and column of 6 by 6 here. This 1.5 is that 1.5. Assume that this 6 by 6 is full of 0, okay? I'm just starting. It's full of 0. I'm just starting to put everything from these two into the bigger matrix. You should repeat this for all the numbers inside this matrix and for all the numbers inside the other matrix. The next one, let's go for, I don't know, this 1. Okay, the 1 corresponds to column 4 and row 3. Column 4, row 3. Here it is. Right? You should do it. How many times you should do it? You have 4 by 4 numbers here, means 16. Another 16 here. 32. 32 times, you should go through all the numbers, put them in the right places. If one cell, this cell, row number 4, column number 2, doesn't receive anything from any of them, you don't have any combination of 2 and 4. Okay, if you don't have, if this cell doesn't receive anything from those, all of those, that's fine. It stays 0. And it has a physical meaning. Deformation, degrees of freedoms 2 and 4. 2 and 4. They are not connected together. So they should be 0. 2 is transversal deformation of this end. 4 is rotation of another element's end. They are not connected. There is no stiffness between these 2 degrees of freedoms. It should be 0. But, for example, this number 4. Where does this come from? 4. It is 3 by 3. We have 3 by 3 here and 3 by 3 here. It receives these 2 and again it receives these 2. They add together, they produce 4 here. If one cell receives a couple of numbers from this procedure, okay, they come into the cell, they add up together with their signs, whatever they are. It has a physical meaning. What does it mean? It means that the degrees of freedom number 3, 3, 3, is the rotation here. It gets some stiffness from element number 1 and some other stiffness from element number 2. It's between the connection between two elements. So it gets some stiffness from this element and from that element. So it has a physical meaning. If you repeat this procedure for whole numbers in these two matrices, I mean, you need to just really do it 32 times, because you have 16 numbers here. If you fill all of these into the big matrix, you will have a 6 by 6 matrix for the whole structure. Still, we didn't comply with the boundary condition. Okay, this is for the whole structure. The mathematic doesn't understand where are the supports, right? Any doubts until now? Everything clear? Right? So. This 6 by 6 again represents deformation 1, 2, 3, 4, 5, 6, forces 1, 2, 3, 5, 6. Okay? Forces from 1 to 4 are external forces, and we have only one non-zero at degrees of freedom number 2. Because the question is this one, we have one external force is 5 kilonewton here. This 5 kilonewton is along number 2, degrees of freedom number 2, it's here, right? If it was a concentrated moment, it was along number 1, right? If you had two forces, okay, you had two non-zeros here. So that's why you have 0, 0, 0, only -5 there. Why -5? Not +5? Because it's upside down. If it was from down to up, it was reverse, it was positive. But because my y prime is from down to top, it's like this: x prime, y prime, z prime. If you had, if you don't have it, what do you do? If you had, for example, something like concentrated moment, let's call it 7 kilonewton meter. This 7 would go along the 1, and this number should be -7. Okay? The rest of the two, these two, what are these two? Q5 and Q6.
Okay, the directions.
What? Directions? Support reactions. Did you say directions or reactions? Reactions, yes.
Okay.
They are reactions. Yeah, you were right. They are reactions because they are support. 5 and 6. See? 5 is support, 6 is support. Be careful for this support. For this support, we don't account for this because we know from the beginning, we know this Fx is 0. And we don't count about axial forces. At the beginning, I said we ignore about axial deformations and axial forces. So Q5 and Q6 are, say, Q5 and Q6. They are support reactions. They are unknown. We don't know they. So they are unknown. These 4 are knowns. What are these? 0, 0. Keep in your mind, this is vector of deformations. This is vector of forces. In the vector of deformation, we have 0, 0 corresponding to these two support reactions. So when you have a support reaction here along the 5, so you should have deformation equal to 0. This is the definition of support. So the definition of support says this should be 0, this should be 0, right? It's always the case. When you have some support, the deformations are 0, known, and the forces are unknowns. You need to calculate them later on. For support, we have unknown support reactions and known displacements. This will be the definition of the support. And last, not least, what are these for D1, 2, 3, 4?
The four forces in the
Forces are in the left-hand side. Deformations are in the right-hand side. F equal to K delta. In the right-hand side, deformations. Left-hand side, forces. Depends which way you're standing, like this. Force, deformation. If you don't remember, just keep in your mind, F equal to K delta. This is for spring. F, K delta. What are Q1, 2, 3, 4? Sorry, D1, 2, 3, 4. Louder. That's correct, louder.
displacement.
Displacements of the degrees of freedom 1, 2, 3, 4. Are they known or unknown? Do we know them or they should be calculated? D1, 2, 3, 4. If we knew them, we'd write the number. They are unknown. And they are the aim of solving this problem. We need to calculate the deformation. This is the stiffness method. I told you that force-based method work with the force, these methods work with the displacement. They aim to calculate the displacement at the degrees of freedoms, right? We want to calculate D1, 2, 3, 4. Okay? When we come to this point, we can say, if you remember, we had this in the truss structures, but because of the long holiday, maybe you forgot some parts. When we come to this point, we just say like this: for those numbers corresponding to the supports, for example, this is 0 for the support. This is fifth line. Just go and eliminate row 5, column 5. This is 0, and this is in row 6. Just eliminate row 6, column 6. Eliminate all the rows and columns corresponding to known displacements, which are usually from supports, right? The remaining part will be something like this. Maybe I can write it here. The remaining part is something like this: 0, -5, 0, 0 is some matrix which is 4 by 4, D1, D2, D3, D4, which are unknowns. This matrix is this part. This goes here. Right? Just eliminate. You're complying with the boundary condition. You're complying with eliminating rows and columns for the boundary condition. And you have 4 unknowns, 4 knowns. The best way is just to inverse this matrix and multiply it by this to get D1 to D4. However, you can use other methods if you like. Just substitute one, in terms of another, whatever. But basically, the best way is to inverse this and multiply by the vector of forces and come up with D1, 2, 3, 4. These are the deformations which were unknown. When we come up to this point, the problem is solved. In terms of deformation, the problem is solved totally in terms of deformations. It means that we know what the deformations are. We know exactly how the structure deforms. Okay? What really you need to have, if you want, is probably support reactions, right? And internal forces of elements. If you want the support reactions, you need to go back and use those rows and columns you eliminated before. For example, Q5 is equal to this line multiplied by this line. Now you have the 1, 2, 3, 4, right? Which means that 1.5 multiplied by D1 minus 1.5 multiplied by D2 plus 0 multiplied by D3 plus 1.5 multiplied by D4. These two are zeros. Q5 and Q6 can be calculated, which are support reactions in those two supports, from those lines that you eliminated before when you were complying with the compounder condition, right? What else you need? You probably need internal forces for elements. You can get back. This was the stiffness matrix for element number 1, okay? So the 4 elements for element number 1 is this matrix A1, only this matrix, multiplied by, this should be the 6, 4, 5, 3, the 6, the 4, the 5, the 3. You have them. You have from 1 to 4. This is 0. You have, this is 0. You have 3 and 4. Just put it there and multiply it. You will get 4 elements at both ends of element number 1. Right? It's easy. When you get the unknown deformation, displacements, you can use them to calculate what else you want for the structure, like support reactions or element forces at both ends. Carefully look at them and if there is any question. Yeah.
I think you already said this, but how do you go from the matrix to the formulas?
From which matrix?
The matrix to the top.
To here?
To these formulas.
To this one?
Yeah. No, I did to the formulas of D1 equals minus.
This one?
Yeah.
I solved it.
Yeah.
Okay, this is unknown. I write it somewhere if I find some places. Let's call it, you know, what is this 4 by 4? This is this one, okay?
After crossing out with the zeros. Okay.
Let's name it K, I don't know what, K total, okay? K total, for example. If you name it like this, D1, D2, D3, D4 is equal to K total inverse multiplied by 0 minus 5, 0, 0. Keep in your mind, when it's 4 by 4, this is 4 by 4, and this is 4 by 1. The multiplication will be 4 by 1. Okay? You need to inverse this. It's like for this equation, I'm multiplying both sides of the equation by K total minus 1. K total minus 1. K total minus 1 multiplied by K total will be unity. Right? This is unknown here, will be K minus 1 total multiplied by the vector of forces. Right? Look at it carefully. I don't move until you're happy with that. Yes.
Once you solve for the one or the two, does that give you the answer in radians or that degrees or?
Good question. Good question. Look at here. D1 is rotational. D2 is transversal. 3 and 4 are rotational. 1, 3, 4. 1, 3, 4 are rotational. They're radian. This one is meter. And if you, no, it's not. It's not parametric like that because we have 5 kilonewton there. If we solve this one like it should be P, L, something like this, you will see that the dimension of this is different from the others. But this number has a dimension, it's not dimensionless. But these 3 are radian and this is meter, if you follow that. Any other question? If really you understand this example fully, you don't have any problem to solve any kind of beams. I think so. That the rest of examples are somehow probably similar. And also your coursework like this. The coursework is, I don't remember exactly. Did it have a spring or not? Or it was just a simple beam with 2 parts?
The beam was like this one.
Did it have a spring?
No.
No, it didn't. Spring was for those people. With this example, you can solve the coursework example very easily. Just with this one, I'm pretty certain. Yeah. But I didn't want to teach this in rush before the Christmas, so I just postponed it to the second part of your course. What is this? This is another beam, just somehow similar to the previous one, but the supports are different. We have a fixed support here. This is a fixed support. This is a roller. And this is a roller. So still we have 2 beams. We have 3 nodes. We have 3 nodes times 2, 6 degrees of freedom. How many degrees of freedoms are constrained? I mean, the deformations are 0.
The 0. Oh, and sorry, wait.
No.
It's only the fixed.
We have 3 supports. And each node has 2 degrees of freedoms, one vertically, one rotational. The left fixed support constrains 2 of them, vertically and rotationally, theta is 0, right? The middle roller, another one, vertically. Another roller, another one vertically. How many together? 4. 4. For it, let's go through it step by step. We have joint number 1, joint number 2, joint number 3. Okay? These are nodes. We have element number 1, element number 2. This arrow means from near end to far. Right? We have degrees of freedoms. I don't write it because it takes messy. Degrees of freedoms are 2, 3, 1, 4, 6, 5. Up to you what sequence you're following. Really up to you. It doesn't matter. It just in background, numbers like this because the author of the book wants to make it beautiful when we get to this point, when we want to eliminate those rows and columns, okay? Everything should be in one side. Otherwise, you need to eliminate one row and column here, one row and column there, and it's a little bit messy. Otherwise, it's okay if you number it some other sequence. So, what is this? So, we have 3 transversal degrees of freedom, 3, 4, 5. We have 3 rotational degrees of freedom, 2, 1, 6, right? This fixed support constrains sorry, it's alarm for my hill. That's why every week it's alarm, but I take it off with it. Yeah. The fixed support constrains 6 and 5, right? Because it doesn't move vertically and it doesn't move rotation. It's a fixed support. Forget about the horizontal because we don't count about that. It's 0. We don't have axial forces. Okay. This roller support constrains number 4 because the middle roller support means node number 2 doesn't move vertically. Again, roller support at the middle means the degree of freedom number 4 doesn't move vertically. The deformation along degrees of freedom number 4 is 0, but not number 1. Number 1 is rotation. It rotates at that point, right? The right-hand side roller means the deformation along which degrees of freedom is 0? Say it.
3.
Good. 3 is fixed. What about 2? 2 is free, can rotate, right? So, again, we follow the same sequence of the previous one. We just assemble K1 and K2. Exactly, I'm filling with this formula. This one. I'm using this 4x4 to fill that K1 and K2, right? These 2 are near end, these 2 are far end. Near end, far end. See, 6 and 5 are near end. Right? I'm just following from that 4x4 matrix, filling here. When we assemble K1 and K2, we need to assemble the stiffness matrix of the whole structure, which should be again 6x6. This doesn't differ from the previous one, rather than the supports. Supports will contribute to elimination of rows and columns, right? Still, we have 6x6 matrix for the whole structure. This is K for the whole structure. Let's call it K total. How we do that? Just write a 6x6 matrix full of 0 and start to place every individual value here into the right place. For example, you tell me which one we can take a look at. This one, minus 12 over L3. It belongs to column 5, row 4. Row 4, column 5, it's here. Isn't it? Let's take a look at this number. This one, 4x4, 4x4. Why this is 24, this is 12? Because it takes another number from 4 here. These 2 both go here, go here. That cell 4 by 4 receives 1 and 2 numbers together, they add up together. Make 24 instead of 12, right? It makes sense in physical sense because the degrees of freedom number 4 is this one. Transversal deformation, vertical deformation along y-axis. So if this, forget about the supports. Until now, we are not talking about the support. It means that this is a continuous beam without any support. It can move along 4. Okay. If it wants to move along 4, this beam resists and that beam resists. So there are 2 stiffness values contribute to this degree of freedom. However, we will eliminate that row and column because we have some support there. But before applying the support, that number 4 gets some stiffness from the left-hand side and right-hand side element because it's at the junction of connection of 2 elements. Right? So again, you have 16 numbers here, 16 numbers here. If you place them in the right places, you will come up with 6 by 6 stiffness matrix for the whole structure. When you're talking about the whole structure, you can say, when you write 6 by 6 full of 0, just write your hints as well, like this, just to be clear where you're putting numbers there. When you are here, you don't need to. You just need to say 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. You don't need to say 6, 5, 3, 5, something not in order. It can be in order because when you say 1, 2, 3, 4, 5, 6, 1, 2, 3, 5, 6, then you say, okay, 1 by 1 comes from here. You know, this can be very beautiful, but there is no sequence for this and this. These 2 depends on what you number here, but this is always like 1, 2, 3, 4, 5, 6. So we have a 6 by 6. This is the deformations. This is the forces. Again, D1 and D2 are unknowns. Why? D1 and D2. Rotations at nodes number 2 and 3 are unknowns.
So if K1 and K2 are different, then the total matrix will be the same. Even if
K1 and K2 would be different in terms of EI or something like that.
No, in terms of, the nodes, things, 6, 4, 1, if they're different, the big matrix will be the same.
Yes, yes. But they go in the right places, For example, this is not, this is somewhere else, but it still goes here, Yeah. Final total K is the same, yes, because it's 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. But this numbering depends on how you number here, right? So D1 and D2 are unknown. D3, 4, 5, 6 are 0. Why? Because of the supports. D3 because of this roller, 4 because of this roller, 5 because of 5 and 6 because of that fixed support. D3, 4, 5, 6 are 0. So apparently Q3, 4, 5, 6 are support reactions. And these 2 are external forces corresponding to D1 and D2. See, in the example, we have only one M0 concentrated here. Because M0, see, it is X, Y, and Z, just to be consistent with the first slide. Okay, that's why we put minus M0 here, because it's clockwise. The convention is counterclockwise. Right? So which rows and columns should I eliminate before going forward? All the rows and columns that are corresponding to supports. All rows and columns that are corresponding to 0 displacements. We have 0 displacements here. At rows 4, 5, 6, sorry, 3, 4, 5, 6. 3 goes away, 4 goes away, 5 goes away, 6 goes away. Only this part remains. Okay? I rewrite it here and have some space. It would be 0 minus m0 equal to EI 8 over L 2 over L 2 over L 4 over L D1 D2. D1 and D2 are unknowns. Everything else is known. So if we inverse this, multiply by this, we come up with D1 and D2. D1 and D2 are the unknown, where the unknown deformations, now they are known, they are solved. When they are solved, the structure is solved. You can calculate whatever further things you need with these known deformations, which are usually support reactions or internal forces of elements. In terms of support reactions, you need just to go back where you eliminated these rows and columns. The Q3, 4, 5, 6 are support reactions. Each one is the corresponding row multiplied by this vector of deformation. To be more clear, Q3 is this number multiplied by D1 plus this number multiplied by D2 plus this number multiplied by 0. Forget about it. This is 0, this is 0, this is 0. So only the first one multiplied by D1, the second one multiplied by D2. Right? Q4 is the same. The first one, forget about it, is 0. The second one multiplied by D2. Q4, Q5. And the last, not least, if you are interested in calculating the internal forces for each element, just to go a little bit further back, here when you calculated individual stiffness matrix for each element. So this matrix multiplied by D5, D6, D4, D1 will give you a vector of 4 at the near end and far end internal forces of element number 1. If you do the same for this matrix, you will get the internal element forces for element number 2 at both and near and far, right? Look at them carefully if there is any question. Today I need to be a little bit early, so we don't go for a break, but we just share here, okay? Everybody at least. We just go through the last example today. Again, we have the same continuous beam, just playing with external forces and supports. In this case, we have different supports, like we have a roller support here, a fixed not fixed, a simple support here and a roller support here. Altogether, we have 4 support reactions, but we work with 3 of them because this is not important to us, this horizontal support reaction. So again, we have 3 nodes, 2 elements. How many degrees of freedom? 6. It's exactly like the previous. 6 degrees of freedom. Number like this, 1, 2, 3, 4, 5, 6. Right? We know that, not for now, we know that how many of them will be eliminated further? 3 of them. We will again have a 6 by 6 and we will eliminate 3 of them because we have 3 support reactions with makes restraints along the degrees of freedoms 4, 5, 6. Right? But they are constrained not to move along the vertical deformations. Right? So again, if we follow the first slide, we can come up with K1 and K2 individually for element number 1 and 2. Keep in your mind, what are these? This is, the first one is near end, the 2 next are far end. These are near end, these are far end. For near end, the first one is transverse vertical deformation, the second one is the rotation. 6 is vertical, 3 is rotation, 5 is vertical, 2 is rotation. Just to be consistent with the first slide, that 4 by 4 that I'm just mapping that here, you know. So if we calculate K1 and K2, we can again go for the whole stiffness matrix, which is 6 by 6. Okay. Again, this is the 6 by 6 matrix, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And you all know how we put all those double 16 numbers into the right places in the big matrix, right? For example, let's take a look. Where does this 4 come from? It's about row 2, column 2. So this goes here. And also this goes here. Because they are row 2, column 2. Right? What about this one? It's row 5, column 5. This goes here, and this also goes here. I mean here. All right? Every number in that one, 16 numbers, another 16 numbers, go to the right places, right? And we have a 6 by 6 matrix here. Further, we need to eliminate the rows and columns corresponding to support conditions, right? We have support conditions for 4, 5, 6. So row 4, column 4. Row 5, column 5. Row 6, column 6. What remains with this? Right? It really remains like 4, 0, minus 4 equal to EI 2, 1, 0. What was it? 1, probably 4, 1, 0, 1, 2. D1, D2, D3. Only in this stage, only the unknown deformations stay in the place. All the zero deformations will disappear, right? Was it one? Right. Yeah. So if you solve this, this is a group of equations actually, 3 equations by 3 unknowns. With whatever you know from math, you can solve it. But basically, the most convenient way to solve this is to inverse this matrix, multiply it by this 3 by 1 vector and come up with D1, 2, 3. If you do that, you will get D1, D2, and D3. Obviously, D1, D2, D3, all of them are radian because all of them are rotation. And if you are interested in calculation of support reactions, what you should do, you should go back to those 3 lines and columns you eliminated. Q4 is this line multiplied by this column. Q5 is this line multiplied by this column. Q6 is this line multiplied by this column. If you are interested to calculating the internal forces of each element, you should go further back to these 2 matrices and say, okay, this matrix multiplied by D6, D3, D5, D2, I'm just following this order, will be F6, F3, what is this? 6, 3, 5. This is F5 and F2. These 4 are for element number 1. These 2 are for near end. These 2 are for far end. Right? Whatever you have defined at the beginning of your example. Right?
For the, you see, for the displacement, for row 5, the 6 by 6 measures, is that you cancel out because it's very small. Why do you cancel out row 5 rotates?
This one. Oh, sorry, it has something. It has settlement. No, it's not very small. It has a settlement at here. It has support settlement. That's why. I didn't see that at the beginning. These are not all 0. So when you have settlement, we had settlement in some previous examples, didn't we? It means that we have a support, but it's in the middle of the river. Water washes out the soil beneath it, and over time it just settles a little bit down. So for these kind of structures, this effect can cause some internal forces. So if I didn't really see that, if everything is 0, we eliminate it. But in this case, we cannot simply eliminate them here in this stage. What we should do is here, when we come up here, this is a 6 by 6 equations in terms of matrix, okay? We can turn it back from matrix form to the regular mathematical form, like writing like this. 6 different equations. The first one is 4 equal to, right? EI bracket. I'm just writing the first row, okay? 2 plus 2d1 plus 1d2 plus 0d3. The next one is 0. The next one is 1.5 multiplied by 0.0015. It's very small, but it's radian. You cannot neglect it. Now, this radian is something. You know, it's not centimeter or millimeter, it's radian. And bracket, okay? We can do the same for the 3 first, 4, 5, 6, okay? For these three, for the first three, this term can go in the left-hand side and combine with external forces and produce something else, okay? Again, you have here for the second one, it goes back, okay? And if you rewrite these first three again in the form of matrix, you will have, where did I do that? You will have something multiplied by d1, d2, d3 must equal to this one. But this is not 4, 0, minus 4. It's something else. It means that the effect of settlement goes to the left-hand side of your equation and combines with the external forces. It means, in a physical sense, it means that the settlement is kind of external force. And it seems so. It seems so that it's a kind of external force. It means that it produces internal forces in your structure. So it's a kind of external force. It goes to the left-hand side and combines with your external forces. If you have 0, it can go just combine to 0. You know, this was the difference of this example. We had this, I think, in the truss structures as well. But the methodology, the solving methodology is the same. We just, it's a small difference when we are eliminating these rows and columns. Instead of eliminating, just write them down like this and rewrite them like, again, in the matrix form, right? Any question? The next example, it has some distributed loads. I haven't taught this one in, let's skip it because we just work with the concentrated loads. It's not very difficult, but I prefer just to skip it. And the last example is really just the repetition of the previous example. Just take a look at it. And next week, we can go to the frame structures. And if you just take a look at your coursework as well, if you have some doubt about how we can apply this to the coursework, just we can discuss about that as well. Because today's lecture is really what you need for the coursework, for that part that we skipped for the beam solution. So for the part 2, you need to solve that with the knowledge of today's lecture, right?
So part 2, would it be the same beam?
Not this beam, that beam that you have in your brief.
Yeah, no, but I mean for the standard, would it be the same beam that we solved for part 1 and the second part?
Yes. Whatever you had in part 1, one section was solved by using a stiffness method. You have already solved it by virtual work or something like that, and ETABS, and another part was solved by a stiffness method. So a stiffness method is this one. You need to use this knowledge to solve that section. And you already have the answers based on ETABS and virtual work, for example, energy method work. So you should have the right answer And again, confirm it based on stiffness methods, right? Okay. Any other question? If not, it's for today. And the class is dismissed. Thank you. Anybody needs the QR code? If not, I'll close. Let's review this.
There's no
So it's strange. It doesn't pop up that window, but we'll check it. First, but I don't see what happened here.
You know, the matrix table, thickness table, but one for over. Are we given that? Or no, you're to be given that, yeah.
Huh? The problem is that I don't have that window that pops up. I don't know what the problem, but I it can be. Okay, yeah. Only send me your ID. I will try to. You can